Hello everyone. So far we have looked at important concepts in understanding recombination, absorption, and how we can compensate between absorption and emission, so that we generate photons out, right, and the rate constants associated with that. And finally concluded from many directions, reconfirmed that you need to have population inversion. So that means you need to have more number of particles at the excited state compared to the ground state particles, atoms or molecules combined together. So in order to achieve that, there are multiple platforms one can use, right. You must have studied about gas lasers, dye lasers in other courses, but in this particular case we are looking at semiconductor type lasers, and particularly whether we can use this in an integrated platform. So let us look at a very simple system of light emitting diodes from a simple PN junction that you can easily make in a semiconductor platform, in a planar circuit platform. So let us look at that. So basically what you want is a light emission from a PN junction is what you are looking for, and this you could achieve on different platforms. And in particular, when we say we want to get it from PN junction from a semiconductor, is through electroluminescence. So this is what you are looking at. So what is electroluminescence? It's basically the input is electric field, right. So you have input electric field, and then the output is a photon coming out. So that is the electroluminescence, right. So this is primarily achieved through spontaneous emission. So this is spontaneous emission process is what we use in this case. Now we need to build the circuit or rather the device in order to get photons generated, right. So the light emission is primarily occurring because of recombination, in particular the carrier recombination in the junctions that we have. So let's quickly recap on the junction. We do not have to go into the detail, because this is something that very basic concept that you must have studied in devices course and introduction to photonics as well. So when you have a simple junction, you create an electric field, right, in this direction, right, and it has a certain width associated with this. So this is the junction we talk about, right. So when you talk about these junctions, right, so this will create a band, a bending, let us say, right. So if this is a position, and this is our energy, the electron energy here. So your band is going to look something like this, and similarly like that, and this is our Fermi here. So this is too large, so Fermi is somewhere here, okay, because this is P plus and this is N plus. So we have our electrons in here, and then we have holes located here, right, and the energy difference that we have between here and here is EV naught, which should be greater than the band gap that we have, okay. So this is in thermal equilibrium, okay. So, in equilibrium we have this very nice simple band diagram, but now we want to make these charges to flow, right, because they are separated. You see, what you want in a system is a population inversion where you have electrons there populated and then the holes are sitting here. In this case, wherever you look, this inversion is not there, right. So, we do not have it. So, one way of creating this is by doing forward bias. So, in this heavily doped P plus and N plus region, we are going to do a forward bias. So, when you do a forward bias, when you apply positive to positive and negative to negative, right. So, that is what we call forward bias. When you do a forward bias, the band bending is now reduced, right. So, the bending is reduced now. So, here we have the Fermi level. So, this is our EFV and then here EFC, and now we have the electrons are trying to flow through the system here and the holes are also here. So, holes can go through. So, this is forward bias, right. So, there is a current injection. So, we have charge injection in this direction, right, and the hole injection in this direction. Okay. So, when you see this particular part, this particular region, right, where we have the junction, you can see here there is a number density difference that we see here, right, but at very high injection current density, right, at the junction or what we call the active region. In the active region, we see a population or a crowding of electrons and holes here, right. So, this injection into this, right, will create the right condition for these electrons to recombine with the holes underneath. So, this recombination is something that we have to enable, and that is done through this forward bias, and this forward bias condition helps you, but we need to have radiative recombination, right. So, this recombination that we have should be radiative recombination. So, what that means is when they are coming down, it should create a photon, right. So, this is what we would like to do, and this generated photon will share the energy. So, this will be close to the band gap energy that we have. Okay. So, this is something that we would like to do when you have a junction. Okay. So, let us look at different configurations, right, of using this PN junction for various light emitters. There are 3 type of light emitters that you could do. One is light emitting diode, and the other one is optical amplifier, semiconductor optical amplifier, and the third type of device is laser diode. There are 3 type of device we can build just by using PN junction. Okay. So, let's look at these junction. The first type is a simple PN junction. We have N type and P type, and I am going to positively bias this. And when we do this, you are going to generate photons in all possible directions. Okay. So, you will generate light. Okay, this is natural because you have the junction here and this junction is going to generate photons. And the next type of device that we are interested in is an amplifier. All right. So, again you have N and P type, we are going to forward bias this, and in this case I am going to put a photon in, I am going to put a photon in. So, there is a photon of energy h nu, but then when it comes out it has more photons of same frequency, and this is in a directional form, right. So, this is what we call optical amplifier, and then you could have another type of device where we create the diode here to be highly directional. The light generation is along only in this direction, right, and the emission is confined within this, and that would result in photons coming out only in this direction. So, this is what the laser diode is all about. All right. So, a light emitting diode that we have here primarily is a spontaneous emissions process. It is spontaneous emission is what you see in a light LED structure, right. But in an amplifier and then a laser diode, you have stimulated emission, right. So, in order to have this process happen in these material, right, we made N type and P type material. We use a direct band gap material. It is important that the material platform should be direct band gap material. So, this will ensure high quantum efficiency of emission. Okay. So, normally we use 3-5 group semiconductors, okay, for this kind of light emitters. So, as already mentioned in our earlier lectures, right, the spontaneous emission is going to be really unpolarized or randomly polarized incoherent, right, light that is going to come out from an LED, right, and the LEDs, they do not have any kind of threshold, right. It starts emitting as soon as you start conducting, right. So, as long as the current is flowing through, you will start emitting light from an LED. Okay. So, the LEDs are much easier to start off, right, unlike the other two. So, we need to understand how much flux is required. So, let me put that important point here. So, LED does not have a threshold current, let us say, right. It starts emitting as soon as the injection current flows, right. So, this is an important thing that you may want to keep in mind. All right. So, once you start generating the photon, what is the efficiency of generation, right. So, you need to understand the internal photon flux. So, what is the internal photon flux? Basically your efficiency related. So, that is phi, right. So, what is internal photon flux? Depends on internal efficiency, injection current times the charge, right. So, this is injection electroluminescence. So, here eta internal is internal quantum efficiency. Right. So, this internal quantum efficiency that we have, it depends on many factors, right, and it is basically given by the electron hole recombination, right. So, when the recombination, the radiative recombination, so this primarily depends on radiative and non-radiative. So, you have two recombination, radiative recombination and non-radiative recombination. So, the light generation primarily depends on how much recombination that you have as proportion to radiative or non-radiative. So, the internal quantum efficiency depends on the radiative recombination to total recombination, right, and radiative recombination to radiative plus non-radiative. Okay. So, the NR is the non-radiative and RR is the radiative. So, this is the factor that defines this internal and external quantum efficiency. The other important factor is about this radiative recombination and non-radiative recombination rates, right. So, they depend on the lifetime of the carriers in the system. Okay. So, what you can write is the radiative and non-radiative lifetimes are going to be important. So, that means the recombination lifetime is inversely proportional to the radiative and the non-radiative rates that we just saw. Okay. So, that is nothing but tau r and tau n r. All right. So, the total recombination lifetime is simple addition of radiative and non-radiative recombination lifetimes. Okay. So, these two are the important factors here, and the internal quantum efficiency can be now written as the lifetimes now. So, non-radiative recombination lifetime to the total lifetime that you have. Okay. So, normally this the internal quantum efficiency for semiconductors are pretty high. So, this can be very large because the lifetimes are very small, right. So, the radiative the total time recombination lifetime can be very small, right. So, just to give you an example, for gallium arsenide, right, your tau r, right. So, the radiative recombination is about 100 nanoseconds, okay, while your non-radiative recombination is also in that same order. So, this would result in a total recombination lifetime of about 50 nanosecond, which would result in internal quantum efficiency of 0.5, which is quite high. All right. So, the recombination, the radiative recombination lifetime are very important to get a good quantum efficiency. For example, if you take silicon, your radiative recombination rate is in milliseconds, while your non-radiative recombination is in nanoseconds, right. So, this would result in radiation total radiative radiation lifetime of in terms of nanoseconds, right. So, this would 100 nanoseconds. So, this would result in internal quantum efficiency of very small. So, this is going to be 10 to the power of -5 or -6. So, this is the reason why silicon is not a good emitter at all, and it is and again it is an indirect band gap material. So, we need to make sure that you use a direct band gap material, at the same time your radiative lifetimes, right, are low enough in order to enable light generation in the system. Okay. So, the internal quantum flux that we saw here depends on your internal quantum efficiency, but at the same time we need to also look at the carrier generation here as well. All right. So, how quickly we can generate these carriers. So, the carrier generation is primarily coming from our injection here. So, we had this injection here, right. So, the how much injection, what is the injection rate we have, based on that we could actually find the internal quantum efficiency, which is related to our injection rate. Okay. So, your internal photon flux, right, phi is related to your quantum efficiency times R times V. So, what is R? R is our carrier pair injection. So, how much injection we have or in other terms electron hole pair, right, per centimeter cube per second, right. So, this is what this injection is, and V is the volume, material volume, how large the material volume is. And if you look at it, finally you can deduce this to our earlier equation, or I times E if we want, right. So, you could write this as injection internal times V times delta n times tau. So, this is another way of writing it, because the recombination lifetime also plays a role in your rate, right. So, that the rate here depends on the change in the number density, right. So, your delta n is a carrier difference, right, because of the injection, and which is equal to V delta n divided by tau r. All right. So, these are all various forms of representing our photon flux. Okay. So, on the whole, this photon flux depends on the number of charge carriers you have, and then your recombination lifetime, right. So, we can just write this as a proportionality constant, and this is basically it. So, your photon flux depends on the carrier density change and your lifetime. So, you want your lifetime to be shorter, at the same time you want your charge injection to be higher. Okay. So, how do we achieve this scenario? So, your recombination rate is intrinsic to the material, but then you can play with this injection. So, the injection or the current the carriers that you have can be increased by putting more current into the system, but you cannot increase the current as you like, because there is a limit to the material itself. So, it will break down because you do not have much carriers to follow through, but you can increase the density of carriers. So, that is something that you can do, right. So, let us look at a very simple diode carrier distribution, right. So, let us look at that carrier here. So, this is our very simple diode, and then your carrier diffusion is going to be, so this is our p side and this is our n side. So, your carrier diffusion is something like this. It is too much. This is carrier diffusion, and this is excess carriers. But instead of having such a big distribution, what one could do is by using an heterostructure. So, instead of having a band like this, so we could have a band structure. It could be like this. So, in this case we have gallium aluminum arsenide and gallium arsenide and gallium aluminum arsenide. So, you can say this is the P side and this is our N side. So, when you have this kind of structure where we are using two different type of material, you can see there is a difference in the band gap that will result in carrier confinement. So, this is our carrier confined. So, this is excess carriers. So, in this particular region you can confine the carriers, and by confining the carriers we are increasing your delta n in this, and by increasing the delta n we could effectively generate photons out of this system, right. And another important aspect of this is the light emission itself, right. The optical field, this is optical field will be only in this particular region. Okay. So, what you see is a light guiding. So, by using this kind of heterostructure we should be able to generate light in this very confined region, so that we can have wave guiding, right. So, this becomes an important stack in order to realize waveguide along with light generation. However, if you take a simple p-n junction, the carrier distribution is very large and you are not having any confinement in the charges and also optical field. Okay. So, an heterostructure is something that is essential if you want to improve your light generation or flux density inside the optical medium. So, with this discussion we have come to a basic understanding of how one could create sandwich of stacks by using different material platforms, for example, a low band gap material and a high band gap material. So, by putting a low band gap material between two high band gap materials, you can create carrier confinement, and this carrier confinement would result in efficient light generation. And the reason for that is you are confining the carriers. Not only confining the carriers, your generation is also confined. You are not generating carriers across the structure, it is confined. But this band gap difference that you have between a narrower band gap and large band gap, you are generating refractive index difference as well. And this refractive index difference is also going to help you in light confinement. You know, the narrow band gap material, they have higher refractive index, right. So, the higher refractive index will confine the light, and that is the reason why in a heterostructure you have light confinement in the narrow band gap material. So, by confining the light and also confining your charges in this region, we can efficiently harness the charge injection. Okay. So, with that understanding, we would like to go to generating these charges and trying to create a cavities out of this. So, that is something that we will see in the following lectures. Thank you very much for listening.